Hello students, welcome to Educate. Today we are going to continue with chapter number 7 of class 12 physics. We will do some important questions and some important concepts. So let's start. As we have seen that in case of LCR circuit, we write this type of impedance triangle in which this is Z, this angle is phi, this is XL minus XC, and this is R. So here Z will be equal to square root of R square plus XL minus XC whole square. And from here if we find tan phi, so it will be equal to XL minus XC divided by R. We can also find cos phi. Cos phi will be R upon Z. This is called power factor. Later on we will see about it. And when we talk about a resonance condition, it means we are referring to the situation XL minus XC equal to 0. So Z equal to R square plus XL minus XC whole square gives Z equal to R, right? And from here we write XL minus XC equal to 0, which gives XL equal to XC, or 2 pi FL equal to 1 upon 2 pi FC, from where we can get the value of resonant frequency. Let's denote F as FR will be 1 upon 2 pi root LC, or angular frequency omega R will be 1 upon root LC, right? So this is basic condition. Now the same thing is shown here. Here graph is shown in which value of here corresponding to different values of omega. The peak values are shown like this is resonant frequency, and these are two corner frequencies like omega 1, omega 2, where current reduces to root 2 times. Correct. Now here there is one important application that you can read, like resonant circuits have a variety of applications. For example, in the tuning mechanism of a radio or TV set, the antenna of a radio accepts signals from many broadcasting stations. The signals picked up in the antenna acts as a source in the tuning circuit of the radio. So the circuit can be driven at many frequencies. But to hear one particular radio station, we tune the radio in tuning. In tuning, we vary the capacitance of a capacitor in the tuning circuit such that the resonant frequency of the circuit becomes nearly equal to the frequency of the radio signal received. When this happens, the amplitude of the current with the frequency of the signals of the particular radio station in the circuit is maximum. It is important to note that resonance phenomena is exhibited by a circuit only if both L and C are present in the circuit. As you have seen that F equal to 1 upon 2 pi root LC means L and C both should be there. Only then do the voltage across L and C cancel each other, both being out of phase, as we have already studied, and the current amplitude becomes Vm upon R, the total source voltage appearing across R. This means that we cannot have resonance in a RL or RC circuit. So I think this is clear. Now we are going to see one example. A resistor of 200 ohm and a capacitor of 15 microfarad are connected in series to a 220 volt 50 hertz AC source. Calculate the current in the circuit. Calculate the voltage across the resistor and the capacitor. Is the algebraic sum of these voltages more than the source voltage? If yes, resolve the paradox. This is one important question. Here, what all is needed is the value of R equal to 200 ohm given, C equal to 15 microfarad, which can be written as 15.0 into 10 power minus 6 farad. Voltage is given 220 volt and frequency is given as 50 hertz. So if you remember, voltage across capacitor will be perpendicular to the voltage across resistors. This angle is 90 degree. So here, if we write this as VC, this as VR, then resulting voltage V net will be equal to square root of VC square plus VR square, and this will be equal to applied voltage. So that we will see. And when we try to find out Z, so in that case we take capacitive reactance square plus resistance square. So here these values are written R square plus XC square. XC is equal to, if you remember, XC is 1 upon 2 pi FC. So here the same thing is written here squared. So if you square it, 2 pi FC whole power, this will become 2 pi FC whole power minus 2 if you square it, x square. F can be written as nu, that does not matter. Now putting values, R is given as 200 square plus 2 pi, pi is 3.14 into F is 50, and then capacitance is given 15 into 10 power minus 6 whole square. If we simplify, we will get 200 square plus 212.3 square, that comes out to be 291.67 ohm. Now we can find the current. So voltage is given as 220 divided by Z, means impedance is 291.67. After evaluation we will get 0.755 ampere, right? Then here we have to find out voltage across capacitance and resistance. So voltage across resistance, since same current flows, so across resistance it will be I times R. R is given as 200 ohm, I we have found as 0.755, so it will come out to be 151 volt. Similarly, voltage across capacitor will be I times XC, so I is 0.755 and here C is given, XC we have evaluated, right? So this 212.3 ohm, we put these values here, and then it becomes 160.3 volt. Now, sorry, if we find the algebraic sum of the two voltages, what do we observe? It will be more. VR plus VC will be more than 220 volt applied voltage, but since they are not in phase, they make 90-degree angle between them. So definitely if we apply Pythagoras theorem, so we will get the same result, right? Here VR and VC, then VR square plus VC square, that gives 220 volt. So this is the phase difference that makes the difference, right? So had they been in same phase, then a rule would have been violated, but it is not the case, right? Now let's proceed. Power in AC circuit, the power factor. So as we have seen here, as I told you, that we can find tan phi, this is XL minus XC, this is R, this is Z, this angle is phi, so tan phi will be XL minus XC divided by R. And we can also find current, maximum current IM will be Vm divided by Z. This is maximum voltage, but RM, you know Vrms, how it is related with Vm. So it will be Vm divided by root 2, that we have already studied. Now we are going to see the power associated. So Here we write P equal to VI. Suppose current differs by voltage with angle phi. So equation of voltage is Vm sin omega t, and that of current it is say Im sin omega t plus phi. Right. Here we can take out Vm and Im, and then we divide and multiply by 2. So inside we will be left with 2 sin omega t plus phi, and then we can apply the formula. What is formula? The formula is, if you remember, here we have already studied in trigonometry, like cos A minus cos B will give what? Will give 2 sine A plus B by 2 sine A minus B by 2. So that thing is being applied here. So we get this result, cos phi minus cos 2 pi 2 omega t plus phi, right? And then the average power over a cycle is given by the average of the two terms in the RHS. We have to find out the average value of these. It is only the second term which is time dependent. Here time dependent term is there. So it will have no contribution, because over one complete cycle this will become 0. So only this term will contribute. So we can say that power is equal to Vm Im divided by 2 and this cos phi, right? And in terms of RMS values, suppose we want to write Vm divided by root 2. This 2 can be split in terms of root 2. So Vm divided by root 2, Im divided by root 2. So this will become Vrms, this will become Irms into cos phi, right? So this can also be written as Vi cos phi becomes I square. We can replace this by I z. So I square z cos phi. So the average power dissipated depends not only on the voltage and current, but also on the cosine of the phase angle. So this depends on, power depends also on cos phi, right? Phase angle phi between them. The quantity cos phi is called the power factor. So you should know about it. And if it is different values, we can assign. When cos phi is 0, in that case power consumption will be 0. When cos phi will be 1, in that case maximum power consumption will take place. So we have already studied that in case of capacitor or inductor, the lag between voltage and current is pi by 2. So in that case there is no power consumption. So in such case it will be wattless current, right? Here same thing is explained here. Cos phi equal to, and no power is dissipated even when the current is flowing in the circuit. This current is sometimes referred to as wattless current. So wattless current is that current in which there is no power loss, right? And in case of LCR circuit, phi is tan inverse xc minus xl divided by r. So we can assign some values. And next case is power dissipated at resonance. In case of resonance, what happens? XL minus XC becomes 0. Phi will not be there. So cos phi will have maximum value. In that case, power will be I square Z or I square R. That is, maximum power is dissipated in the circuit, right? So I think you have understood the basic concepts. Now we are going to analyze some questions. For circuits used for transporting electric power, a low power factor implies large power loss in transmission. Explain. So we have seen that P equal to IV cos phi, where cos phi is the power factor. Here they are saying low power factor implies large power loss. So here, to supply a given power at a given voltage, if cos phi is small, we have to increase current accordingly, right? Because power is fixed. So when this is small, then we have to increase these things. But this will lead to large power loss, I square R in transmission. You know, power loss is I square R if current is increasing. In that case, I square R will have more value, and hence there will be more loss. Now, second point is, power factor can often be improved by the use of capacitor of appropriate capacitance in the circuit explained. So we know cos phi equal to R upon Z, and current I lags the voltage by an angle phi. Then power factor will be this, that we can improve the power factor tending to 1 by making Z tend to R. If Z is tending to R, so this value will be approximately 1. So let us understand with the help of a phasor diagram. So for this, we are going to take help of phasor diagram. So here, same thing is explained. This is voltage, this is current. So two components have been taken. One is IP and that is IQ. So here, let us resolve I into two components, IP along the applied voltage and IQ perpendicular to the applied voltage. IQ, as you have learned in this, is called the wattless component. This will be wattless component because cos 90 will be there, and since there is 90 degrees, so power loss will be 0. Now, so IP is known as the power component because it is in phase with the voltage. This will be IP, this IP will be in phase with voltage, so definitely there will be power loss. Now, it is clear from this analysis that if we want to improve power factor, we must completely neutralize the lagging wattless current IQ. So this should not be there by an equal leading wattless current. So in order to cancel this component, there should be another current in opposite direction. So this can be done by connecting a capacitor of appropriate value in parallel so that IQ and IQ dash cancel each other and P is effectively IPV. What is purpose? So here our purpose is to cancel this IQ component. So for that purpose, we connect one capacitor, so that provides just opposite value, and hence these two components get cancelled and only V times IP is left. Right. Now let's see next question. Here we have a sinusoidal voltage of peak value 283 volt and frequency 50 Hz is applied to a series LCR circuit in which R is given as 3 ohm, L is 25.48 millihenry and C equal to 796 microfarad. Find the impedance of the circuit. You remember impedance? Impedance is given by Z equal to square root of R square plus XL minus XC square. So we need XL. XL is 2 pi FL. Frequency is given 50, 2 pi, so 2 into 3.14 into frequency is 50 into L is given as 25.48 millihenry means 10 power minus 3. So this will come out to be 8 ohm. Now we need XC. XC is 1 upon 2 pi FC. We put the values 1 upon 2 pi 3.14 into frequency 50 and C is given as 796 microfarad 10 power minus 6. This comes out to be 4 ohm. Now we apply the formula Z equal to R square plus XL minus XC whole square. XL minus XC, XL is 8, XC is 4. So 3 square plus 8 minus 4 square, that gives 5 ohm. Correct? Then we have to find out phase difference. As you know very well, XL tan inverse XC minus XL, because this is from that formula tan phi equal to XC minus XL divided by R. It can be opposite also, XL minus XC or XC minus XL, that depends. So here tan inverse 4 minus 8 divided by 3, which comes out to be minus minus 53.1 degree. Then phi is negative, so current in the circuit lags the voltage across the source. That is. Then we have to find out what is power dissipated. So power dissipated will be I square R because there is no power loss with capacitor or inductor. So I is Im divided by root 2. So 1 upon root 2 times Im 283 divided by 5, that is 40 ampere. So we have got the value of this I, and then we put here resistance is given 3 ohm in the question. So power will be equal to 4800 watt. Then power factor we want to find out. So we have already evaluated the degree value. So cos phi, cos of minus 53.1 degree. So by using calculator, we will get this value 0.6. Now there is another question. Suppose the frequency of the source in the previous example can be varied, right? in previous example, we have taken frequency as 50 Hertz. What is the frequency of the source at which resonance occurs? We have to find out resonant frequency. So for that condition, as you know, XL minus X equal to 0, that gives omega 0 or omega R equal to 1 per root LC. So in previous case, we are having L as 25.48 millihenry, so 10 power minus 3, and capacitance was given as 796 microfarad. So after putting these values, we get this angular frequency as 222.1 radian per second. And frequency, since omega equal to 2 pi f, so f can be found f or nu, so nu can be found as omega 0 divided by 2 pi. So omega 0 we have got 221.1 divided by 2 into 3.14 hertz. That comes out to be 35.4 hertz. Correct? Now, in case of resonance, what happens? Net resistance means net impedance becomes equal to resistance, so Z will be R. And RMS current at resonance condition will be V upon Z. V is 283 divided by root 2. This is peak value, so that is why RMS value is found. And then resistance 3 ohm. So this comes out to be 66.7 ampere. Now power dissipated at resonance will be P equal to I square into R. I we have found 66.7 ampere. Square it and put the value of resistance, that is 3. So this comes out to be 13.35 kilowatt. So I think you have understood. Now there is one important question. Question says, at an airport, a person is made to walk through the doorway of a metal detector. For security reasons, if she or he is carrying anything made of metal, the metal detector emits a sound. On what principle does this detector work? Here, main concept is resonance condition, and other things we can see. The metal detector works on the principle of resonance in AC circuit. When you walk through a metal detector, you are in fact walking through a coil of many turns. The coil is connected to a capacitor tuned so that the circuit is in resonance. When you walk through with metal in your pocket, the impedance of the circuit changes, resulting in significant change in current in the circuit. This change in current is detected, and the electronic circuitry causes a sound to be emitted as an alarm. So I think you have understood, and we have studied about the transformer. We have seen different type of transformer like step up, step down. Here diagram is shown, primary and secondary coils, and either we can take this type of transformer or we can take this type of transformer, but the flux must be linked. There should not be flux loss, right? And voltage across primary will be ES equal to minus NS, number of turns in primary, then change in flux d phi by dt. Similarly, voltage across, this is voltage across secondary. Voltage across primary will be EP minus NP d phi by dt. Flux change will be same. So after equating, we will get ES upon EP will be NS upon NP. And here, the voltage are taken, induced voltage and applied voltage are taken as same. Here concept is given, you can go through, and we have already studied about it. This is just a quick recap. And step down, step up transformers also we have studied, in which if number of turns in secondary are greater than number of turns in primary, then we say that transformer is step up, and if secondary turns are less than primary turns, then it will be step down. And then there are different types of losses in case of transformer, like flux leakage. So let's read these points in detail. So flux leakage is the first type of energy loss. There is always some flux leakage. That is, not all of the flux due to primary passes through the secondary due to poor winding. This is an important point. And it can be reduced by winding the primary and secondary coils one over the other. So first type of transformer will be preferred. Then resistance of the winding. Of course, the wire used for winding has some resistance, and so energy is lost due to heat produced in the wire, that is I square R. In high current, low voltage windings, these are minimized by using thick wires. Then comes eddy currents. You have studied about eddy currents. The alternating magnetic flux induces eddy currents in the iron core and causes heating. The effect is reduced by using a laminated core. Then comes hysteresis, means magnetization and demagnetization. The magnetization of the core is repeatedly reversed by the alternating magnetic field. The resulting expenditure of energy in the core appears as heat and is kept to a minimum by using a magnetic material which has a low hysteresis loss. And one more point, the large scale transmission and distribution of electrical energy over long distances is done with use of transformers. The voltage output of the generator is stepped up so that current is reduced and consequently I square R loss is cut down. You have to keep in mind this point. It is then transmitted over long distances to an area substation near the consumers. There the voltage is stepped down. It is further stepped down at distributing substations and utility poles before a power supply up to 40 volt reaches our homes, right? Then let's have a quick revision of everything that we have studied. And alternating voltage V equal to Vm sine omega t. Here Vm is maximum value. Applied to a resistor or drives a current I equal to Im sine omega t. The two are in same phase. So Im is Vm upon R. And then comes for an alternating current I equal to Im sine omega t passing through a resistor R, the average power loss P due to Joule's heating is 1 by 2 Im square by R. To express it in the same form as the DC power P equal to I square R, a special value of current is used. It is called root mean square value, RMS value, and that is given by I equal to Im divided by root 2. Or we can write 0.702 into Im. Similarly, if we write RMS voltage, so we write Vm maximum voltage divided by root 2, that comes out to be 0.707 of maximum voltage. So, and we have P equal to Vi or I square R. Then an AC voltage V equal to Vm sin omega t applied to a pure inductor drives a current in the inductor I equal to Im sin omega t minus pi by 2. What does this mean? It means current lags voltage by pi by 2. And in this case, Im will be Vm upon XL, where XL equal to omega L or 2 pi FL. That is called inductive reactance, and the unit of inductive reactance is ohm. The current in the inductor lags the voltage by pi by 2, and we have studied that average power supplied to an inductor over one complete cycle is 0. Then comes next point, and AC voltage V equal to Vm sin omega t applied to a capacitor drives a current in the capacitor I equal to Im sin omega t plus pi by 2. Here what does this pi by 2 indicate? It indicates that current leads voltage by pi by 2, and maximum current can be written as Vm upon Xc. Xc is capacitive reactance, which is given by 1 upon omega C. The current through the capacitor is pi by 2 ahead of the applied voltage. As in the case of inductor, the average power supplied to a capacitor over one complete cycle is 0. Then comes for a series RLC circuit driven by voltage V equal to Vm sin omega t, the current is given by I equal to Im sin omega t plus phi, where phi is to be determined. Phi can be found by using formula tan phi equal to Xc minus XL divided by R, or just to reverse. Now, here Im will be Vm applied voltage divided by R square plus Xc minus XL whole square. This is Vm is maximum value, and here this is maximum current, right? IRMS and VRMS can be found accordingly, and Z equal to R square plus Xc minus XL whole square. This is called impedance of the circuit. The average power loss over complete cycle is given by P equal to Vi cos phi, where cos phi is called power factor. Power factor in case of pure inductor or capacitor will be 0. In that case, power loss will be 0, but in case of resistance, it will have maximum value, so that we can. Now, wattless current, it means there is no power loss, and the phase relationship between current and voltage in an AC circuit can be shown conveniently by representing voltage and current by rotating vectors called phasors. A phasor is a vector which rotates about the origin with angular speed omega. The magnitude of a phasor represents the amplitude or peak value of the quantity voltage or current represented by the phasor. We have seen the analysis of an AC circuit is facilitated by the use of a phasor diagram. Then comes transformer. A transformer consists of an iron core on which are bound a primary coil of turns Np and a secondary coil of turns Ns. A primary coil is connected to an AC source. The primary and secondary voltage are related by formula Vs upon Vp must be equal to Ns upon Np, and current is just opposite. Is upon Ip will be equal to Np upon Ns. If the secondary coil has a greater number of turns than the primary, the voltage is stepped up, that is Vs will be greater than Vp. This type of arrangement is called step-up transformer. If the secondary coil has turns less than the primary, we have a step-down transformer. So we have seen the complete summary here. RMS voltage is V, its dimension is given, and we can find its expression. RMS current is given. These all things are important for your exam purpose. Here, even quality factor is evaluated. It was earlier in your syllabus, but now it is removed. But for competition purpose, you must know that quality factor Q is given by voltage across inductor and divided by voltage across resistance. So we can find this omega 0 L divided by R equal to 1 upon omega 0 CR. So, and which will be equal to cos phi. Phi is phase difference, that you know. This here power factor is equal to cos phi. So here questions based on this quality factor you can do. They are given in competition section, and here the same thing, some important concepts are given, like when a value is given for an AC voltage or current, it is ordinarily the RMS value. Whenever you are evaluating, when you are given a question, in that case you have to consider the given value as RMS value, and then suppose you need maximum value, in that case you have to multiply it by root 2. For example, if 240 volt is given, so we have to convert it to maximum voltage. For that we multiply by root 2 to get 340 volt. The power rating of an element used in circuit AC refers to its average power rating. You must have seen that on bulb it is written like 60 watt 220 volt. So we can use that for calculating the resistance. The power consumed in an AC circuit is never negative, of course. Both alternating current and direct current are measured in amperes, but how is the ampere defined for an alternating current? It cannot be derived from the mutual attraction of the two parallel wires carrying AC current as the DC ampere is derived. And AC current changes its direction, right? So with the source frequency, and the attractive force would average out to be zero. So the AC ampere must be defined in terms of some property that is independent of the direction of the current. Joule heating is such a property, and there is 1 ampere of RMS value of alternating current in a circuit if the current produces the same average heating effect as 1 ampere of DC would produce under the same conditions. This is one important point. This is needed for different type of competitions, so you must know this. In an AC circuit, while adding voltage across different elements, one should take care of their phases properly. For example, if VR and VC are voltage across R and C respectively in AC circuit, then the total voltage across RC combination will be VRC equal to VR square plus VC square, and not VR plus VC, since VC is pi by 2 out of phase of VR. So we have studied about these things. Then, though in a phasor diagram, voltage and current are represented by vectors, these quantities are not really vectors themselves, right? They are scalar quantities. It so happens that the amplitudes and phases of harmonically varying scalars combine mathematically in the same way as do the projections of the rotating vectors of corresponding magnitudes and direction. The rotating vectors that represent harmonically varying scalar quantities are introduced only to provide us with a simple way of adding these quantities using a rule that we already know as the law of vector addition. And then there are no power losses associated with pure capacitances and pure inductances in an AC circuit. The only element that dissipates energy in an AC circuit is the resistive element. Then in a RLC circuit, resonance phenomena occurs when XL equal to XC, or omega 0 becomes 1 upon root LC. For resonance to occur, the presence of both an L, C elements in the circuit is must. With only one of these L or C elements, there is no possibility of voltage cancellation, and hence no resonance will occur. And then final point is the power factor in RLC circuit is a measure of how close the circuit is to expending the maximum power. And then in generators and motors, the role of input and output are reversed. In a motor, electric energy is the input and mechanical energy is the output. In a generator, mechanical energy is the input and the electrical energy the output. Both devices simply transform energy from one form to another. And a transformer step up changes a low voltage into high voltage. This does not violate the law of conservation of energy. The current is reduced by the same proportion. Keep in mind, this is important question. This is one important concept you can say. And that is all. So I think you have understood the chapter fully. Thank you for watching. Team Educate